Hello everyone. Now we discuss here Seifert Van Kampen theorem. So we know that if U and V are two subspaces of X such that X can be written as their union, and these two are open subsets of X, and the intersection of U and V, that is path connected space, and let us take some point x naught in the intersection of U and V. Then these two groups, ux naught and pi1 vx naught, images of these two groups in group pi1 xx naught under the homomorphism induced by inclusion, means we take two inclusion maps J1 from U to X and J2 V to X. Then we have two different homomorphisms. One is J1 star, which is from pi1 ux naught to pi1 xx naught. Similarly, we have J2 star, pi1 vx naught to pi1 xx naught. Now, under these two mappings, the images of these two groups, pi1 ux naught and pi1 vx naught, in the group pi1 xx naught, that generate the group pi1 xx naught, which means we can say that pi1 xx naught, this is generated by image of J1 star, means J1 star of pi1 ux naught, and image of J2 star, means J2 star pi1 vx naught. So pi1 xx naught, that will be generated by these two groups, which means every element of pi1 xx naught can be written as can be written in terms of finite number of elements of these two groups. Now in this section, in this theorem, Seifert Van Kampen theorem, we will prove that pi1 xx naught, this is completely determined by these two groups, and the third group is pi1 u intersection v x naught. So this is completely determined by these two groups and this group, and various homomorphisms of these groups which are induced by inclusion maps. So firstly we state the theorem Seifert Van Kampen theorem. So this theorem says when X is U union V, where U and V are open sets in X, and we assume that U, V and U intersection V all are path connected, and if we take a point x naught in U intersection V and H be any group and we assume two different homomorphisms, one is pi1 from the fundamental group of U to H, and other is phi2 fundamental group of V to H. Let these be homomorphisms. Now suppose J1, J2, I1 and I2. these be homomorphisms which are induced by actually inclusion maps, and these be homomorphisms as in this diagram. Induced by inclusions. So what is the diagram? Now here we have pi 1 u intersection v x naught, 2 pi 1 u x naught. This is group H, pi 1 x x naught. So this is our I1, the homomorphism induced by the inclusion map from U intersection V to U. Similarly, this is I2. This is J1, homomorphism induced by inclusion map from U to X. Similarly, this is J2. And these are the given homomorphisms phi 1 and phi 2. Then this theorem says if phi 1 circle I1 is equal to phi 2 circle I2, which means if these two compositions, this composition and this composition are equal, then there is a unique homomorphism capital phi from pi 1 x x naught to H, such that now this mapping capital phi, the existence of this mapping we have to prove. We have to prove that there exists this unique homomorphism capital phi such that capital phi circle J1, this is phi 1, and this circle J2, that is phi 2. That means we want to prove that these two triangles, one is this and other is this, these two are commutative triangles. Phi circle J1, this composition is phi 1, and this composition, that is small phi 2. Now basically this theorem says that if we have any homomorphisms phi 1 and phi 2 which are compatible on U intersection V, then they induce a homomorphism of pi 1 x x naught into H. So we are saying if phi 1 intersection I1 is equal to phi 2 intersection I2, which means if they are compatible on U intersection V, means if we go from U intersection V to H either via this, by going from firstly U intersection V to U and then to H, and otherwise if we go from U intersection V via V, means firstly we go from U intersection V to V and then to H. So if we go from U intersection V to the group H, if we go from fundamental group of U intersection V to the group H either via U or via V, both are same. Means phi 1 circle I1 and phi 2 circle I2, they are same. Then this induces a homomorphism of pi 1 x x naught to H. Now, firstly, uniqueness part is very easy. Firstly, we will prove uniqueness. If such a mapping capital phi exists, then that is unique mapping. So now we know that pi 1 x x naught, this is generated by images of J1 and J2 as we have earlier discussed. Now the value of phi, capital phi, on the generator J1, G1. Now we know element of this is generated by images of J1 and J2. That means every element of this group can be written as a finite product of elements of the groups, finite product of elements of the images of J1 and J2. That means each generator of the element of pi1 xx naught, that is of the type J1 G1 and J2 G2. So if we take a value of phi on the generator J1 G1, then that must equal to phi 1 G1, because we have given that phi 1 circle I1 that is equal to phi 2 circle I2. And similarly, if we take value of phi on the generator J2 G2, so that must equal phi 2 G2, because if a mapping phi exists, then these two triangles on the right hand side of this diagram, they are commutative. So it means phi is completely determined by phi 1 and phi 2. So it is unique. So now we prove the existence part. So for the existence part, we define some notations firstly. For a given path f in space X, we will denote by this square bracket of f path homotopy class of f in space X. And we will, if f lies in U, because U is a subset of X, if f lies in U, then we will use this notation fu to indicate a path homotopy class in space U, path homotopy class of f. This is also path homotopy class. Similarly, if f lies in V, then fv, this is path homotopy class of f in V, and f u intersection V, this is path homotopy class of the same path f lying in u intersection V. So this theorem can be proved in many steps. So step 1 of the proof. Now here we will define a map row. In this step we will define a map row which assigns to each loop f based at x naught, which lies in either U or in V, an element of the group H. Means this row is defined on F, where F is a loop based at point x naught, lying in either U or V. So if f is a loop lying in U, then we will define it by phi 1 of fu, because if f is a loop lying in U, then its homotopy class that will be denoted by this symbol. Similarly, we define a row of f, that is phi 2 of fv if this lies in V. So we write here if f lies in U and if f lies in V. So we define a set map. Now we have to prove that this mapping is well defined. Now if F lies in both U and V, means if it lies in intersection of U and V, then what will happen? If F lies in U and V, then phi1 of Fu, that is phi1 of I1 Fu intersection V. Now why we can write this? Because this I1, this is the homomorphism induced by inclusion map, and under inclusion map this mapping is defined like this. If F is a loop lying in U intersection V, then its homotopy class will be mapped to homotopy class of F in U. Similarly, phi2 of Fv, this is phi2 I2 of Fu intersection V. And it is given to us that phi1 circle I1 is equal to phi2 circle I2. So these two elements are equal. It means phi1 at Fu and phi2 at Fb, they are equal. That means if we define rho by this, if F lies in U, and rho defined by phi2 of Fb if F lies in V, and if F lies in both U and V, then these two are same. That means rho is well defined. So it means rho is well defined map. Now we will prove that rho satisfies these two conditions. Number one, if the homotopy class of F in U and homotopy class of G in U, they are same. Or secondly, if their homotopy classes in G, they are same, then rho F is equal to rho G. Means if two paths, they have same homotopy classes either in space U or in V, then their images under rho, they are same. And second condition, we will prove that if both F and G lie in U or both lie in V, then rho F star G, this is rho of F into rho of G. So if both lie in U or both lie in V, then rho is linear on their product, basically. Now, first of these conditions that holds by definition, because if homotopy class of F and homotopy class of G are same, then rho F by definition, it is now firstly we suppose that they lie in U, then rho is defined by phi1 of Fu, and rho of G, that is defined by phi2 of Gu. And we are saying that Fu and Gu, they are same. So if they are same, then their images under the mapping phi1 and phi2, they are same, because phi1 circle I1, that is equal to phi2 circle I2. So this Fu is this, basically this is equal to I1 of Fu intersection V. This is I1, I2 of G at U intersection V. So if these two are equal, then phi1 circle I1 and phi2 circle I2, they are same. So that's why rho F and rho G are same by definition. Similarly, we can prove when they lie in V, then also phi1 is equal, rho F is equal to rho G. So this is true by definition. And the second condition that holds because phi1 and phi2 both are homomorphisms. So rho of F star G, that is basically, let us say F and G both lie in U, then rho of F star G, that will be phi of F star G in U. So it will be phi1 of F, phi2 of G, because phi 1, because phi 1 is a homomorphism. Similarly, if that lies in V, then because phi 2 is a homomorphism, then also this condition is true. So this is rho F into rho G. So these conditions are true for the mapping rho. Now we will prove the second step. In the second step, we will extend this mapping rho to a mapping sigma, and sigma is defined on each path lying in U or V to an element of H. Now in the first step, we have defined rho on the loops, on the closed paths based at point x0. But in the second step, we extend this mappings to all the paths, not only the closed paths. So we extend here rho to a map sigma, and this sigma assigns to each path F lying in either U or V an element of H. The rho assigns to each closed path F lying in either U or V an element of H, and we will prove that this sigma, this is defined in such a way that it is extension of rho, and also this map sigma satisfies the condition 1 of step 1, satisfies condition 1 of step 1, and it satisfies condition 2 whenever F star G is defined. Because in the first step, F and G both are closed paths based at x0. So F star G is always defined. But here we are taking F and G to be any paths lying in U or V. That means F star G is defined only when endpoint of F is equals to starting point of G. So whenever this is defined, this condition 2 is also satisfied here. So here, firstly we choose for each x in X, we choose alpha x is a path from x0 to x. Our point x0, that is fixed. And now we have this type of situation. Say this is U, this is V, and the intersection portion, this is U intersection V. Now we have this point x0 lying in U intersection V. So we are, let us say point x is here, point y is here, then the path from x0 to x, let us say this is alpha x, path from x0 to y, this is alpha y. So for any x in X, we take alpha x to be a path from x0 to x. Since we are assuming that this space is pathwise connected, so that's why we can take path alpha x. Then for any path F, so this alpha x, we choose this path to be, alpha x is a path from x0 to x, choose this as follows. So how we choose this path? Now if x is equal to x0, अगर अब if x x0 के ही equal है, तो alpha x is chosen to be constant path at x0. Then alpha x is constant path at x0. If x lies in U intersection V, now because we are assuming that U intersection V is the path connector space, then we take alpha x to be path in U intersection V. As shown in this diagram, we have taken this path, which whole path lies in U intersection V, not the path going like this Okay, so if X lies in U or V, then we take if X lies in U or V and not in U intersection V, just like this, Y belongs to V but not in the intersection portion, then alpha X is chosen to be a path in U or V. Means if, for example, this Y lies in V, then whole path from X0 to Y that lies in V. Similarly, if we take a point in U, then the path from X0 to Z, whole of this path lies in U. So we choose paths alpha X to be like this. Then for any path F in either U or in V, we define a loop. And a loop is given by LF. For the given path F, we define a loop LF again in either U or in V. So let us say that F is a path from any point X to point Y. Suppose this is our path F from X to Y. Then we want to define a loop which is based at X0, so that we can extend the mapping rho, because rho is defined on paths based at X0. So for this path F, how we define a loop based at X0? We define LF to be alpha X star F star alpha Y bar, means reverse of path alpha Y. So so this path will be defined by alpha X. So firstly we go from point X0 to X through the path alpha X. Then we go along F from X to Y. Then we go along reverse of path alpha Y from Y to X0. So this will be our path which is based at X0. Now X is the initial point of this point. So this is X is initial point of F and Y is initial point of Y is final point of Y. So we write here where X is initial point of F and Y is terminal point of F. So if X and Y are endpoints of F, then we define LF to be alpha X star F star alpha Y bar. So now we define mapping sigma. Now sigma F is defined to be rho of LF, because rho is defined on loops based at point X0. So rho of LF is well-defined mapping, and we define sigma F to be rho of LF. Now firstly we show that sigma is extension of rho. So for that, if we take F to be loop based at point X0, lying in either U or V, then what is LF? Now because F itself is a loop based at X0, so it will be just constant path at X, because the starting and ending points of F, they are just X0. So it will be alpha X0. By definition, it will be alpha X0 star F star alpha X0 bar. So alpha X0 is just the constant path at point X0, so it is EX0. So EX0 star F star EX0, where this EX0, this is constant path at point X0. So for this loop F based at point X0, LF is this. So what is rho of LF? Now rho of LF is rho of EX0 star F star EX0, but this is the identity element of the fundamental group. So it is just equal to rho of F. So it means sigma is just an extension of rho. Now we prove that it satisfies the conditions. Now to check firstly condition 1. Now if we take F and G be paths which are path homotopic in either U or in V, then condition 1. So if F and G are paths which are homotopic in U or in V, then LF and LG, they are also homotopic, because if F and G are homotopic, then we multiply alpha x on the left hand side and multiply alpha y bar on the right hand side of F, and then LF and LG, they are also homotopic to each other. So then LF and LG, these are also homotopic, again in space U or in V, because we have defined LF to be in U if F lies in U. So we apply the condition 1 on LF and LG. That means rho of LF is equal to rho of LG if these two are homotopic. That means sigma F and sigma G are same. So condition 1 is proved for the mapping sigma. So now we will check condition 2. Now we take F and G to be arbitrary paths such that F star G is defined, which means F of 1 is equal to G of naught. So let F and G be arbitrary paths either in space U or in V such that F of 1 is equal to G0. Then what is LF star LG? Now by definition, LF is alpha x, F, alpha y bar. So here we are assuming that endpoints of F are x and y. Now since we have assumed that endpoint of y is also the initial point of G, so basically we take G to be a path from y to, let us say, z. So this LF star LG, this will be a loop from x to z. Then what is rho of LF star G? Now F star G is the path from x to z. So L of F star G, that will be just alpha x star F star G star alpha z bar. So this will be this LF star LG, this will be path homotopic to LF star G. So this is rho LF star LG, and that will be rho of LF by the second condition on mapping rho. So rho of LF is sigma F, sigma G, and this is basically sigma F star G. So sigma F star G is equal to sigma F into sigma G. So condition 2 is also proved for the mapping sigma. Now we come to step 3. In step 3, we finally extend this mapping sigma to a mapping tau, which assigns to any arbitrary path f of x an element of h, which satisfies again the conditions 1 and 2. So in the first step, we have defined a mapping rho which assigns to each loop, either lying in space U or lying in V, an element of H. In the second step, we extended that mapping to mapping which assigns to every path in either U or in V an element of H. Now we will extend this to map which assigns to any path in X an element of H. So now here we are taking paths which need not be either in U or in V. They can be in space X. Means some of that path may be in U and other part may be in V. So that type of paths. So finally, we extend sigma to a mapping tau, which assigns to an arbitrary path f of the space X, an element of H. And also this tau mapping that will satisfy the conditions 1 and 2. So first condition will be here, if the homotopy classes of F and G are same, then tau F is equal to tau G. And similarly, the second condition is tau of F star G is equal to tau F into tau G whenever F star G is defined. So firstly, for any path F in space X, we convert that path into paths lying in either U or in V so that we can extend mapping sigma to rho. And let us see how. Let this be space U, this be space V, and suppose we have a path F from X to Y. Say this is X, this is Y. Now we have this type of path, say, in space X. So we choose a partition because if F is a path like this, so basically F is a mapping from 0, 1 to X, such that F of 0 is X and F of 1 is Y. So we partition this interval 0, 1 into subintervals. And we choose this partition in such a way that image of each subinterval that either lies in U or in V. So let us take, this is the subdivision of 0, 1. Let's say this is S0, S1 up to Sn, like less than 1. Sn is equal to 1. So we have divided the interval 0, 1 into n subintervals such that image of each subinterval means firstly image of S0, S1. Let us say image of S0, S1 is this, but this particular portion of F. Then image of S1, S2, that is this portion. Image of S2 to S3, that is, let us say this. Then image of S3 to S4, then let us say that is this. So we take like this the images of all the subintervals, and we have chosen these in such a way that image of every subinterval that completely lies in either U or in V. For example, this completely lies in U, this, and this completely lies in U. Now this particular portion that lies in U as well as in V. Similarly, this lies in V, this, and so on, they lie in V. So for any given path F in X, we choose a subdivision, say this S0 less than S1 less than Sn of the interval 0, 1, such that F maps each of the subinterval into either U or V. And let Fi denote the positive linear map of the interval 0, 1 to the interval Si minus 1 to Si followed by F. What it means? It means Fi is, firstly we map the interval 0, 1 to the interval Si minus 1 to Si linearly, and then we map this interval to x by the mapping f. So this is positive linear map from 0, 1 to this interval, and this map, this to x, the mapping f, means basically f1 is this path, f1 is this path, similarly f2 is this path, f3 is this path, and so on. Then, because of our choice of this subdivision, each fi, that is a path either in u or in v. And second thing, the path f, that will be just f1 star, f2 star, fn. Now, because we have to define tau to be the extension of sigma, which satisfies condition 1 and 2, so we have to define tau in such a manner that tau of f, it should be equal to sigma of f1, sigma of f2 up to sigma fn. So we define like this. So define tau f to be sigma f1, sigma f2, sigma fn. So with this definition, we can easily prove that tau is extension of sigma and it satisfies conditions 1 and 2. So firstly, we show that this definition, this is independent of choice of subdivision. So let us say we change the subdivision, we add some point in the subdivision, and we add this point in interval si to si minus 1. So suppose we have added a point p in the interval si minus 1 to si. Then what will be our new tau of f? So the factor sigma fi, that will be changed. So suppose now fi double dash and fi dash, these are mappings which are positive linear maps of 0i to map point p to si, followed by f. This similarly fi dash, this is a mapping, the positive linear map from si minus 1 to p, followed by f. So this tau f for the new subdivision, that will be sigma f2, sigma fi minus 1, and sigma fi will be replaced now by sigma fi dash, sigma fi double dash, then sigma fi plus 1 up to sigma fn. So this is our new definition of tau. But now if fi, because we have assumed that all the fi's, they are either lying in u or in v. So if fi lies in u, then fi dash and fi double dash both lies in u, and in that case sigma of fi, that will be sigma of fi dash, sigma of fi double dash, because in the previous step we have proved that if this is a path lying in either u or in v, and if the product fi dash and product fi dash star fi double dash, that is defined, then sigma of fi dash into fi double dash, that is equal to sigma fi dash into sigma fi double dash. So because of this relation, the two definitions of tau, uh, one is for the previous partition and other is for the new partition, they are same. So it means tau is the definition of tau that is independent of the choice of the partition. So by the definition of tau, we can easily check that this is an extension of sigma, because if f is a path completely lying in either u or in v, then we choose the trivial partition, which is equal to 0, 1 itself. In that case, tau f will be sigma f, and it satisfies the two conditions also. So up to this, we have defined a mapping which maps each path in space x to an element of H, and it satisfies two conditions: that if two homotopy classes are same, then their images are same under tau, and secondly, this is a if f star g is defined, then tau of f star g is equal to tau f into tau g. That means it satisfies the condition to be a homomorphism. Actually, in the next steps, we will prove the conditions 1 and 2 for this mapping tau. And in the last step, we will complete the proof of the theorem. Okay, so I will explain step 4, 5, and 6 in the next video.